Okay, so today we're going to look at equilibrium. Basically, an equilibrium is about balance within a system. So if we have a look at a general reaction with A lots of A, B lots of B, going to C lots of C, and D lots of D, our Kc, which is our equilibrium constant with respect to concentration, will be the products divided by the reactants. And the stoichiometric coefficients appear here as the indices. So this C goes up here, the D goes there, and so on. But remember, it's always the products over the reactants. If we take an example here, write the equilibrium constant for the reaction of 2 carbon monoxides, 1 oxygen, giving 2 carbon dioxides. We have to look at our products here and our reactants here in the denominator. So again, our CO2, because there was 2 lots of CO2, we have 2 here as a power. There's only 1 oxygen, so oxygen doesn't have a power with its concentration. There's 2 lots of carbon monoxide, so there's a power of 2 there. We can also write the equilibrium constant in terms of pressure. Okay, so we could have the partial pressure of CO2 and the partial pressure of carbon monoxide and the partial pressure of oxygen, and they've got the powers there for those species. There is a relationship between Kc and Kp, and that is that Kp equals Kc times RT to the change in the number of moles of gas. For this to work, the pressure is in atmospheres, and R is the gas constant. But instead of being the 8.314 value, it's the 0.08206 value. So let's consider this following equilibrium. We've got SO3 gas going to SO2 gas plus a half O2. Our equilibrium expression is going to have O2 to the power of a half, SO2, and SO3 in the equilibrium expression. Now, if for this particular reaction we have a Kp of 0.4207 at 350 Kelvin, how would we calculate Kc? Well, if we go back to our original equation, we see that there's 1.5 moles of gas in the product. So there's 1 mole plus a half mole. Okay, and there's 1 mole on the reactant side. So as I've got here, 1.5 moles of gas on the right and 1 mole on the left. So the difference in these two is 0.5. So 1.5 take away 1 is 0.5. So this will be our delta N value. So I'll rearrange this equation and I get Kc equals Kp divided by RT to the power of 0.5. I'll put in these values. So 0.4207 was our original Kp value. Our 0.08206 litres atmospheres per mole per Kelvin is our gas constant, and a 350 is the temperature. I put those in and make sure I've got it to the power of a half, and I get this for Kc. Okay, equilibrium expressions do not have units, so don't worry about trying to balance numbers of moles and atmospheres and things. We don't worry about units at all with equilibrium expressions. And we also do not have liquids or solids. So in this reaction here, we've got sodium plus oxygen going to sodium oxide. Only the oxygen is the gas. These are solids, and so they're not included in the equilibrium expression. So our Kc is 1 over the concentration of O2 to the power of half, or if we looked at it in terms of Kp, we'd have 1 over our partial pressure to the power of a half. Okay, let's have another look at an example. If we have HCl plus our H2O going to H3O plus Cl minus, the H2O is a liquid, so it doesn't appear in the equilibrium expression. These are all aqueous species, and so they appear. Okay, let's now have a look at Kw, pH, and pOH. A particular equilibrium expression for H plus and OH minus ions is this water product, Kw. Okay, and so our Kw is equal to 10 to the minus 14 at 25 degrees Celsius. So H plus times the OH minus, so protons times hydroxide is 10 to the minus 14. If we have neutral water, then these two things are equal, and so I could replace the OH minus with H plus, so it would be H plus times H plus, which gives us H plus squared. So H plus squared would equal 10 to the minus 14. So then if I want just H plus on its own, it's going to be the square root of 10 to the minus 14, which is 10 to the minus 7 moles per litre. So I hope that makes sense. So in neutral water, this is 10 to the minus 7, this is 10 to the minus 7. You multiply 10 to the minus 7 by 10 to the minus 7, you get 10 to the minus 14. But of course, even when the water isn't neutral, Kw still holds. So let's have a look at an example of that. Question: the H plus of a solution, H plus concentration of a solution of HCl aqueous is 0.072 moles per litre. Calculate the OH minus concentration in the solution. So again, we write out a Kw like this. Now I can put in the concentration of H plus, which is 0.072, and I've got my hydroxide, which I don't know, and that equals this water product. So now I have the hydroxide going to be equal to 10 to the minus 14 divided by 0.072, and I get this value here. So that's the concentration of hydroxide. The larger the H plus is, the smaller the OH minus is going to be. Now pH. You've probably all heard of pH, but what does it mean? pH is actually the negative log of H plus concentration. So the best way to see this is to do an example. Calculate the pH of the HCl aqueous solution where H plus is 0.072 moles per litre. Okay, so here I do the pH equals negative log of this concentration of H plus, and when I do that in the calculator, I get 1.14. Try and make sure you can do that on the calculator. Okay, all you do is you put in, so I've got my negative button here, negative, and then log of 0.072, and that will give me 1.14 as the pH. Also, if you do it here for water, if you're wondering why pH of 7 is neutral, the reason pH of 7 is for neutral water is because if you look at 10 to the minus 7 and you put that in your calculator, so the negative log of 10 to the minus 7 will give you a pH of 7. Okay, so try that in your calculator as well. But that's why neutral water has a pH of 7. It's because the concentration of the H plus is 10 to the minus 7. The important fact is that pH plus pOH equals 14. So in the same way that the hydroxide times the proton concentration equals 10 to the minus 14, you can also derive that the pH and the pOH equals 14. The pOH is just going to be the negative log of the OH minus concentration. So the same sort of relationship. So acids and bases. So an acid is a substance that donates protons. A base is a substance that accepts protons. Also, some bases can be viewed as hydroxide donors. So if you have a look at HCl, HNO3, which is called nitric acid, and sulfuric acid, H2SO4, they're strong acids. They dissociate readily, which means they dissociate to a large degree. So HCl is going to split up into H plus and Cl minus. H2SO4 can actually split up into two H pluses and a sulfate. Okay, some strong bases are potassium hydroxide and sodium hydroxide. Again, the hydroxide the hydroxide can be released from potassium hydroxide, and what happens is that hydroxide can then interact with an H plus and accept it. So that's why it's a proton acceptor to give you water. So another base here would be ammonia. Now ammonia can interact with water to give ammonium, which is NH4 plus your OH minus. So this is an example where this ammonia is accepting a proton. Okay, let's have a quick look at conjugate acids and bases. So if we have a look at nitric acid for our acid, it's an acid because it's going to be a proton donor. What it means is, and this is where you have to be careful, when it goes over the other side of the arrow, it donates a proton. Okay. The base, it's a base because as it goes across the arrow, it accepts a proton and gives you the ammonium ion. And so here, so forget the word conjugate for the time being. This is a base, this NO3 minus, because as it goes across the arrow, it accepts a proton to give you HNO3 again. The NH4 plus, as it goes across, it's going to donate an H plus to go back to NH3. So it's about what is going to happen. A lot of people make a mistake here and they think that this must be an acid. They think this is the acid because it's already donated the H plus. It's not about what it's already done. It's about what it's going to do. Okay, it's what it's going to do when it goes across an arrow. So it's going to absorb a proton when it goes across an arrow. So it's a base. Okay, so again, this is the acid. It hasn't donated the proton yet. The proton's still here, but it's the acid because it's going to donate the proton when it goes across. So here we have another example of CH3. By the way, the conjugate just means that it's part of it, it's paired. Okay, so the acid always has a conjugate base, and the base always has a conjugate acid, which is, as you can see, when they go back and forth across, there's a donation of a proton or accepting of a proton. So let's have a look at acetic acid with hydroxide. The hydroxide is going to remove that H from the CH3 COO H species here, leaving just the acetate anion and forming water. Okay, so here's the acid because it's going to donate the proton when it goes across. It's going to lose a proton. So that's the acid, and this is the conjugate base because when it goes back it'll absorb a proton. The hydroxide here is the base because it's going, as it goes across, it's going to accept a proton. But then the water is actually the acid because when it comes back it's going to donate that proton, so it gets back to OH minus. So again we have the base, conjugate acid, acid, conjugate base. So with equilibrium constants for acids we call them Kas. A for acid. So the Ka for acetic acid is 1.8 by 10 to the minus 5. Determine the pH of a 1.2 mole per litre solution of acetic acid. So here we have acetic acid going to CH3 COO minus plus H plus. If we start with our 1.2 mole per litre, we're going to lose some amount. We're not sure what we're going to lose, but we're going to start with 1.2 and remove X amount. And then this is going to, because it's a one-to-one stoichiometry, this is going to gain X, and this is going to gain X as well. So the acetic acid splits up into the acetate and the H+. If the acetic acid split up and gave you 2 protons, then it would be 2X here, plus 2X. So another table that's commonly used in chemistry is where we set up the different concentrations and we have the initial concentrations. So initially there's 1.2 mole per litre of acetic acid, 0 of acetate and 0 of H+. Then we look at the change. So we're going to lose X amount, so minus X. We're going to gain X, gain X. Equilibrium is just when you add these together. So it'll be 1.2, take away X, plus X, plus X. Then we do our equilibrium expression. So we have H plus times the acetate concentrations divided by the acetic acid concentration. And so that's, as we saw from the previous table, there's X amount of H plus, X amount of acetate. And then in the denominator we have our 1.2 minus X, because that's the equilibrium condition for the acetic acid. So from here we have X squared divided by 1.2 minus X, and that equals our equilibrium constant. This can be solved as a quadratic, but it takes a lot of work, and what we can do is make an assumption. Since Ka is a lot less than 1, so Ka, this number is really 0.000018. That means that when I take away that X, this is going to be very much just like 1.2. If you get 1.2 and take away 0.000018, you'll still be left with, pretty close to 1.2. And so we can just simplify this denominator term just to give 1.2 again. So that simplifies this equation a lot. And so now all we have to do is take that 1.2 and multiply it to the other side. So we have X squared equals this, and then X is going to equal our square root of the 1.2 by 1.8 by 10 to the minus 5. And that gives us this value for our H+. The pH is going to be a negative log of that number. So negative log of 0.0046 gives us 2.33. Okay, so now let's have a look at reactions of acids and bases. If you put acids and bases together, you're going to get salt and water. Okay, so let's have a look at sodium hydroxide. That's our base. We add it to hydrobromic acid. It's going to give us sodium bromide. As an aqueous species, this is just going to be sodium plus cations and bromide anions just floating around, and liquid water. So just remember that an acid and the base gives you a salt and water. Okay, so the question: a mixture of 2 moles of carbon monoxide and 2 moles of water was allowed to come to equilibrium in a 10-litre flask at high temperature. If Kc is 4, what is the molar concentration of H2 in the equilibrium mixture? Again, we're going to set up a table like this, like we had before, but we're going to have to work out the concentrations. So we know that there's 2 moles in 10 litres. So our concentration is 2 moles in 10 litres. C equals N over V. And so we know that each of the CO and the H2O is going to be 0.2 mole. So in our initial conditions, we've got 0.2 moles of carbon monoxide, 0.2 moles of water. Then we have a look at our concentration of CO2 and H2. They're both 0 because nothing's happened yet. So then our change is going to be minus x, plus x, plus x. So all up, we have 0.2 minus x, 0.2 minus x, and x. When we put this into our equilibrium expression, remember these terms are going to be the numerator terms, and these terms here are going to be the denominator terms. And so we have this. X times x, 0.2 minus x, 0.2 minus x, gives us x squared over 0.2 minus x squared, equals 4, because that was our Kc, our equilibrium constant. So now we just take the square root of both sides. It's a very convenient problem, this one. Not all of them are so friendly. So we take the square root of x squared, gives us x. We take the square root of 0.2 minus x, all squared, that gives us this, 0.2 minus x. Take the square root of 4 and we get 2. So then we can rearrange this to give x equals 2 times 0.2. So it'd be 2 times the 0.2. Take away the 2 times the x. Okay. Rearrange that again and we have 3 lots of x equals 0.4. X equals 0.1333. And which to 2 sig figs is 0.13. Now, in this case, H2 does equal x. You've always got to be careful to make sure that you go back and have a look. So here, H2 equals x. It's possible if you have a different stoichiometry. For instance, if there was a 2H2 here, this would actually be a 2x. So you've always got to be careful once you solve x to make sure that you go back and see what H2 equals. In this case, H2 does equal x, so that's fine. Okay, this brings us to Le Chatelier's principle. So Le Chatelier's principle basically looks at how the ratio of products and reactants changes with respect to different conditions. So the only change that changes an equilibrium constant is temperature. So unless it's the temperature that's actually changing, the constant must remain constant. So changes in pressure and volume and concentration do not alter the equilibrium constant. Consider 2 lots of SO2 gas plus O2 gives 2 lots of SO3 gas. Okay, so will an increase in pressure cause the more reactants to form or products to form? So what will happen is we look at our equilibrium constant and we see that we have SO3 squared, so the partial pressure of SO3 squared, we have our partial pressure of SO2 squared and our partial pressure of O2 just the way it is because of the equation. So there's a 2 here, 1, 2. Okay, so we take that into account with our equilibrium expression. All up, there's a power of 2 relationship in the numerator and a power of 3 relationship in the denominator because 2 plus 1 gives us 3. So if I double this, if I doubled the pressure, I would end up with a factor of 4 up the top and I would end up with a factor of 8 in the bottom. 4 times 2 because it'd be 2 squared times 2. Again, you can just add up the indices in the expressions. So there's a total of power of 2 up the top and a total of 2 plus 1 is 3 in the bottom. So if I doubled the pressure, the numerator would increase to give us 4 lots of what we had, and the denominator would increase to give us 8 lots because it would be 2 to the power of 3. I hope that makes sense. Basically, if you just look at the one that has the most, the highest power there, that will help you understand what's going on. So the denominator has the highest power, if you like, the largest power, and so any increase will increase the denominator more than the numerator. But K has to stay constant. So the only way that K can stay constant is if it makes more product. Okay? So so I hope that makes sense. If you double the pressures, the denominator is going to get much bigger than the numerator, and that's not the way it should be. And so it just pushes the reaction pushes the reaction forward to make more product, to get rid of some of that reactant because the reactant's too abundant. Okay, so now let's have a look at another one. So for the same equilibrium, what effect will increasing the container volume have? Well, if we increase the container volume, we decrease the pressure. Okay, so we decrease the pressure, that will have a greater effect in the denominator. So the denominator, so the greater effect will always come with what's got the highest powers, the largest powers. And so the denominator has the largest powers, so a decrease in pressure will affect this the most, which means it will reduce the most, which means that the numerator will be bigger than what it should be compared to the denominator. So that means it will push it backwards to make more reactant. Okay, so the denominator will decrease more than the numerator, more reactants will form to compensate. Okay. In the previous example, will an increase in O2 concentration shift equilibrium left or right? If you start making the O2 bigger, this number gets bigger. This makes the denominator bigger than what it should be. So the only way that can maintain the constant value is if it starts reacting these things to use some of them up and make more SO3. Okay, so so it would shift it to the right. This will make the denominator bigger. Some O2 and some SO2 will be used to make more product. So it shifts right. Okay, let's have a look at exothermic reactions. Remember how I said temperature is the only thing that will change the equilibrium constant value. So exothermic reactions are reactions that release heat. Now, when you have a reaction releasing heat, if you heat it up, it's going to be harder for that reaction to release heat. It's trying to release heat in a hotter and hotter environment, which hinders it. And so what will happen is your K will decrease, which will cause the reactions to shift more to the left. So less product will form because K itself will decrease when an exothermic equilibrium is heated. When you have an endothermic equilibrium, that's an equilibrium where it likes having heat because it absorbs heat. So if you start increasing the temperature of an endothermic reaction, it will actually be favoured for products because it likes to absorb heat to make products. The more heat you give it, the better off it will be, and so K will increase. Okay, so just try and remember those ones. Again, temperature is the only thing that will affect K, and it depends on whether it's exothermic or endothermic. Let's have a look at our solubility product. Let's consider calcium fluoride. So it's not very soluble, but when it dissolves in water, we have calcium fluoride solid splitting up into calcium 2+ and 2 fluoride ions. Again, we have a special K for this. It's KSP, SP being the solubility product, and so we have our calcium ions times our fluoride ions squared because of the 2, and we do not consider this in the equilibrium expression because it's a solid. So we don't consider it because it's a solid. So let's have a look at an example. So given the KSP for calcium fluoride is 4 × 10⁻11, calculate the solubility of calcium fluoride. We just use F, which would be a formal concentration. We don't know what it is, but it doesn't matter. It's just an amount that it's irrelevant. But the fact is that it will lose some of its S. It will lose S amounts of itself when it dissolves. Say if we started with 15 moles and we lose 0.1 mole, okay? Then that would be 0.1. If you lose 0.1 there, then you must gain 0.1 here, and you must gain 2 lots of 0.1 because 2 lots of fluoride form for every one of these. So you look at the stoichiometry. For every one of these, we get one of these. So if it loses an S, it must gain an S of calcium 2+, but it must gain 2 lots of S of the fluoride. Okay, so a fluoride must be 2 lots of S. Then you just forget about exactly what we've done. You go back to what the KSP expression is. So forget about the S's. This is the step we have to be careful with. So we go back to what our equilibrium expression is in the first place. That equilibrium expression, if you remember, was looking at the calcium 2+ and the fluoride. The calcium 2+ and the fluoride squared, okay, because of the 2 there. Then after that, then you can put in the S terms. So then once you've got those there, you put in the S for the calcium and you put in the 2S for the fluoride. But remember, you still got to square it. That's why I told you to ignore what you've done before, because you need to look at it as 2 separate approaches. One approach is you're looking at the equilibrium constant itself. Then you put in the values as they would happen from the stoichiometry considerations of losing some S amount. Okay, and so then here, so we have S times, this will be 4S squared in this parentheses here, so then we get 4S cubed. Then you have this and you need to solve for S. So you solve for S and you get 3.3 × 10⁻12. So the solubility is going to be 3.3 × 10⁻12 because that S value, if you remember, that S value is the amount that's dissolving. We start with a solid and that S is the amount that's dissolving, that's being lost into the solution, which is exactly what the solubility is about. So solubility is going to be that amount that dissolves in there, 3.3 × 10⁻12. Okay, so let's have a look at another example. With KSP for aluminium sulfate, it's a 69.2, which is a reasonably large value. And so we calculate the solubility of that Again, we have a F minus S. Now here, there's 2 aluminiums coming off, so we have 2S for that. For every one of these, we have 2 lots of these. We also have 3 sulfate, so it will be a 3S. Then again, I ignore the S's and stuff and just put out what my KSP is, which is the aluminium squared, the sulfate cubed, just looking at these here, so I just ignore that part there and just go back to the basics. Then I can put in the 2S and the 3S in these terms here. So it will become 2S squared, 3S cubed. Okay? So then I end up with a total of 108 S to the power of 5 equals 69.2, because that's my KSP. So then I solve for S, and so 69.2 divided by 108, then I've got to take the 5th root, so that's the same as having a power of a 5th there, if I take the 5th root of both sides. So I hope that makes sense to you. I get 0.128 mole per litre, and so in other words, the solubility is 0.128 mole per litre. Okay, again, because the S is indicating how much of it comes off, how much of it goes from the solid into the solution. So let's have a look at and we briefly covered this before, but our delta G and our equilibrium constants. So delta G equals minus RT natural log of K. A chemical reaction that has an entropy of 27.8 joules per Kelvin per mole and an enthalpy of minus 22.9 kilojoules per mole, determine the equilibrium constant for that. And so, given that the temperature of the reaction is 298.15, so I've got to work out delta G first. So delta G equals delta H minus T delta S. So I put in my delta H minus 22.9. Now here's a tricky thing. I've got by 10 to the 3 here, and that's because I want to keep it in joules per mole. So remember here it's in kilojoules per mole. We don't want that because the entropy is in joules per mole. So you want to use the same units all the way through so that it's consistent. So I've got to convert this kilojoules per mole to joules per mole. Then I take away T, which is my temperature, multiplied by my entropy term here. And so I do that, and I get this value, minus 3.119 by 10 to the 4 joules per mole. Then I know that my delta G equals minus RT natural log of K. So I'm going to have to do a bit of rearranging there. And so I have natural log of K equals minus delta G on RT. So K equals E to the power of minus delta G on RT equals E to the minus 3.119 by 10 to the minus 4 joules per mole divided by the R and the T together. So I've got my R. Now the R here has to be 8.314 joules per Kelvin per mole. Okay, so remember that, don't get mixed up with that. And now 298. The other R will not work here at all. So that gives me my K of 2.91 by 10 to the 5. Okay, so another thing to consider with equilibrium reactions is that they're not static. At equilibrium, products are still being formed and reactants are still being formed. So even though the equilibrium looks like it's stationary, what's really happening is products are still getting formed and reactants are still getting formed, but the rate of their formation is equal. So the rate at which products are getting formed is exactly the same rate as which products are also getting broken back into reactants. Okay, so it's important because that's a fundamental understanding of equilibrium, is that the products are still getting formed all the time. You know, don't think that it's just stopped. The reaction hasn't stopped. It's just that it's got a forward and reverse rate that are happening, at the same time. Okay, so again, just to sort of have a bit of a refresher on the pH and the pOH thing, the pH of a solution is 4.8. What is the pOH? Okay, so pH and pOH, as I said before, equals 14. So a simple calculation here would be pOH equals 14 minus 4.8, which gives you 9.2. So I'll leave it there for our topic of equilibrium. Please give me an email if you have any questions about that. Follow the textbook closely and work through the examples in the ACS book. That's going to be extremely helpful to put together what I've had on this video. But again, if you have any other problems you can't solve, please email me and I'll get back to you as soon as I can. Okay, thank you.